Thank you very much for coming to our today talk. For those who are the first time here, this is Parya Trillium Foundation, the first Iranian community center in the world. It's a charity organization, federally registered since 2002. And I'm honored to welcome Dr. Cumrun Vafa, who has been very kind to join us for our last night fundraising, which was a great help and honor for us, Iranian community and the Torontonian. Just very short and brief about Dr. Vafa. Cumrun Vafa was born in Tehran, Iran in 1960. He attended Alborz High School before leaving for the United States in 1977 to continue his education. He attended MIT, where he received a BS degree in physics and mathematics in 1981, and he pursued graduate studies at Princeton University, where he received his PhD in 1985. While in Princeton, he met the future life fellow student of Farina Sartre. I'm honored that she is also here with us tonight. He came to Harvard in 1985 as a junior fellow at the Harvard Society of Fellow and was appointed as a full professor in the Department of Physics at Harvard University in 1990, and he currently holds the chair of the Hollis Professor of Mathematics and Natural Philosophy at Harvard. He the oldest science chair in the United States. Cumrun Vafa's main area of research is string theory, which tries to unravel fundamental principles of physics. He is well known for his joint work with Andrew Strongdale in establishing thermodynamic properties of the black holes anticipated by Stephen Hawking. Cumrun Vafa has received numerous prizes and recognition for his works on theoretical physics, including the 2017 Breakthrough Prize in Fundamental Physics. In 2008, the Eric Medical of ICTP, and the prize for his work on mathematical physics for American Mathematics Society, as well as American Physics Society. He is member of the National Academy of the Scientific Sciences and the World, as well as the American Academy of the Arts and Sciences. Afarin and Cumrun are proud parents of three sons, Farzan, Kion, and Nikon. Before I ask Dr. Vafa to join on the podium, there are two organizations who has invited their guests and their members to this event who would like to give a few minutes. Can I ask them to join me here?
Thank you, Mr. Tabrizi. I want to welcome everybody and members of Northrop Physics Group, also Shanaf Group. Thanks for coming. And I have to thank Dr. Vafa as well, because he's short stay in Toronto. He accepted to give us this presentation, and I hope that everybody enjoys it. Thank you.
So thank you very much for inviting me to give a talk here. I'm grateful for this opportunity to give a talk here at Parya Foundation. It's also a great opportunity for me to give this talk to those who are enthusiastic about physics and mathematics in general, but who may not be experts in it. So that's the main audience I have in mind now. So it's going to be a general talk. And also I need your participation. So it's going to be more, it's going to be more interactive. So I hope you will help me in terms of answers to some of the questions that we may have. So my area of physics is related to a lot of math. And in fact, math and physics have had a beautiful history of interaction over many, many millennia, I mean at least a few thousand years. And things are going on still at a rapid rate as we speak today. So it's a very dynamic interaction between these two subjects. So to just give a perspective about it, perhaps we should start with a while back where Greek mathematicians and philosophers thought about the relations between math and geometry on the one hand and the relation of that with nature. So they were expecting that symmetries of Platonic solids, for example, there are these 5 Platonic solids, have something to do with basic ingredients that represents fundamental aspects of how the universe works. They were already trying to connect geometry, in this case symmetric objects, with basic elements in nature. So air, earth, fire, and etc. So they were trying to see some relations there. And this kind of relation continued during the rise of the Islamic civilization, where the scientists tried to connect further and understand more about geometric aspects of what there was in the universe. Biruni is an example of it, who measured in particular the radius of the Earth to an unprecedented accuracy just by going over the mountain and looking at the horizon and seeing how much the angle differs from the horizon. And knowing the height of the mountain he climbed, he came up with the formula for the height of for the radius of the Earth with a measurement which was very accurate. And they also found explanations. I mean, it's hard to believe, but can you believe 1,000 years ago they had found out what is the height of the atmosphere? And you might think, how could they possibly know that there was a finite atmosphere? How they figured it out? The idea is very simple. They noticed that when the sun goes down, even though when the sun goes down, the sky doesn't get dark immediately. It takes at least a couple hours. And so they figured that the light is still somehow getting to where we are. So if you think about the top of the Earth where we are, the sun takes a while for it to disappear from the top of the sky. So how long it takes gives you a measure about what's the height of the atmosphere. And from that, they had an estimate about what the height is. And their answer was to within a 20-30% accurate from back all with this very simple calculation. Remarkable, 1,000 years ago.
And what's the number?
30% of the accurate value. So, anyhow, this continued and got more and more advanced with the more modern developments of science. Newton, he came up with beautiful applications of mathematics, and in fact, he invented calculus to try to explain some of the laws of physics, mechanics in particular. And that's a well-known example of it, how mathematics can help physics. And then also mathematicians, like Gauss, was thinking the other way. He had learned that Euclidean geometry is not the only thing possible, and you can have a situation where, for example, if you have a triangle, the angles do not add up to 180 degrees, at least mathematically. So he actually speculated, could it be that our universe is also curved a little bit? That is, if you kind of get a triangle and you add the angles, maybe it's not 180 degrees, even though the triangles you draw on a piece of paper usually add up to 180 degrees. He thought that maybe if you have a bigger triangles, it may not add up. So he went on top of 3 mountains and looked at different directions at the top of the other mountains from each mountaintop and formed the angle and added up these 3 angles to see if they add up to 180 degrees or not. So if it wasn't adding to 180 degrees, it would say that the space is curved. Well, he found that it added up to 180 degrees to the accuracy he could measure, so he didn't find any curvature as we speak today. But he was trying to apply ideas from mathematics to the actual world. So it was a little later where it was found actually that this is going to be important, but it had to wait for a while. Maxwell studied aspects of electricity and magnetism, and these beautiful aspects of these laws encapsulated by beautiful formulas. The details don't matter. Main thing he discovered was that there must be waves, electric and magnetic waves, moving with speed which was close to what they had thought was the speed of light. So he postulated that maybe light is moving electromagnetic fields. Again, ideas from mathematics led the way in identifying light as electric and magnetic fields moving. Then mathematician Riemann came along And he thought about maybe these geometries, which are not Euclidean and they are curved, maybe they are relevant for unifying electricity and magnetism. So he was thinking, again, ahead of his time. This is about a century and a half ago. And then finally Einstein came and he used Riemannian geometry in 3 spatial dimension and 1 time dimension, in other words 4 space-time dimensions, and he found a way to reinterpret and extend Newton's ideas about gravity to a much more geometric theory, where gravity is because of reactions of the space to curvature. So curvature of space and the reaction of the space to where you have a matter became the reason you have gravitational force. So again, geometry played a crucial role in reinterpreting what gravity even means. And then, shortly after Einstein's theory, Kaluza and Klein tried to extend this from 3 space and 1 time dimension to 4 spatial directions and 1 time, where the 4th space they took to be a circle, a tiny circle. So they would think that at each point in space, you have a circle, and using that, they try to give a unification of gravity and electric forces. So they found a way to kind of combine them together. Now I come to my area of research, which is string theory. Now this is the continuation of these developments that then started already in the last century. It's already about 50 years old, this subject. So physicists continue thinking about various questions, and it led to an idea which is called string theory, and it's today we view it as one of the fundamental candidates, the main candidate we have for unifying fundamental forces and particles into one framework. All the forces and all the particles can be described in terms of this theory. And it tries to describe the physics from the smallest scales, the tiniest scales that you can imagine, a trillionth of the size of an atom. That's the smallest size scale they can be in physics. It turns out all the way to the size of the universe. So it encompasses the smallest as well as the largest scales conceivable. And the basic postulate of string theory is that the main ingredient, main particles, fundamental particles, are not point-like, but actually they are loop-like, like a string. Extended objects, one-dimensional objects, which are called strings. So you think about, for example, the nucleus of the atoms having proton, which is made of 2 up quarks and 1 down quark. But in string theory, instead of these up and down quark to be viewed as particles, you think of them as strings. An up quark is one string, another up quark is another string, and then you have another down quark, which is another string. So you can have these kind of strings, which would be the fundamental entities in the theory. And the way they interact, the 2 strings will come together and join and to make 1 string. So this is the way that the strings can interact. You can make out of 2 strings a single string. So that is the nature of the interaction of the strings. And of course, you can go backwards in time. Namely, a string can come and split to 2 strings. And all the particles are the same object. Basically, a string and different vibrational modes of a string give you different particles. This area is very mathematical and involves many abstract ideas. In fact, one of the key facts about this theory is that the number of spatial dimensions is not 3. So we usually think about x, y, and z, 3 different directions, as our spatial directions. This theory says you have to have 6 more spatial directions. Now, you might ask, where are these 6 extra dimensions? I only see 3 directions. What are the other 6? The idea here is that these extra dimensions are so tiny that's hard to see with naked eye. They are kind of so tiny that you can kind of average over them. So you can think at each point in space, these little circles, 6 different directions, that they are hard to see, and this will be needed for the consistency of the theory. Now, what is going on in these extra 6 dimensions will tell you what's happening in our big spatial directions. So it's actually important to understand them. But this is going to be a very mathematical theory, and it is quite non-trivial to understand how you think about these extra dimensions. So So you can think about the space like this. At every point in space, you have extra directions, which are like these spheres or circles, which are these tiny, tiny bubbles you want to think at each point in space. Now, what is my aim in this talk? So, the highly mathematical aspects of string theory is typical of many attempts to connect physics with reality. And can we illustrate the physics-math link by some simpler ideas? I think you appreciate how complicated the thing was beginning to look in my transparency, and perhaps you were worried what's going to happen to the rest of this talk. So I think I want to relieve you. The rest of this talk is going to be much more basic. And this was basically to motivate you that even though the ideas that we deal with are very mathematical, nevertheless, I want to illustrate that many ideas of mathematics, which are simple, are deep and important for physics. So that's what's going to be the aim of this talk. What do we learn about simple ideas in mathematics, and in particular ideas which are encapsulated by simple mathematical puzzles? What can mathematical puzzles teach us about physics? What nuggets of truth can we learn by simple ideas in mathematics? That's my main aim. So I'm going to give you a number of examples about this connection, and I will really need your help with answering these puzzles. So we will start with the first concept. In physics, symmetry and conservation laws are very important. Symmetries, you say, well, of course, I know symmetries, left, right, yes, I know up, down, could look symmetric, yes, good. So now I need your participation in the following puzzle. Imagine you have two buckets of paint, one green and one white, same size. And you pour one little cup from one bucket to the other and stir it and put the same amount back to the first one, and then we'll ask you a question. So in fact, it's good perhaps to see it visually. So imagine we have these buckets, right? There's a green paint. You take a small cup, pour it with green paint, and you put it into this white one. Okay, good. And you stir it. See, it's different color now. Then you take the same amount and you pour it back to the first one. Magical hands do it. Okay, good. And of course, again, you stir the other one, so it's mixed. Now, this is the question that we need to answer. So the answer that I would like you to give to me is, which container has the higher concentration of the other color? Does the green container have more white in it, or the white one has more green in it? Is the question clear, first of all? Yes? So I'll give you just a second to think. I don't want you to rush. And then I'm going to ask for people to raise their hands about the alternatives. So we first took one from the green, put it in the white, and then from that mixture, we put it back into the green. Okay? How many think the green has more white in it? How many think the white has more green in it? Okay. How many think they are equal? Okay, so the majority of you think that the white has more green into it. And let me say why perhaps that is a reason one might think that, is that you put a cup of pure green and you put it in that white. So it was pure green. And now you mix it, and from the mixture you put back in green. So some of the greens might go back to the green, so you would naturally think the green has less white than the white has green. Now, this shows that it's a very natural way to think that way, but unfortunately it's incorrect. Now, you might say, okay, well, it's strange. Why is it correct and incorrect? And this is where symmetry comes to the rescue. Symmetry principles cleans your mind. And I'm going to explain to you how using symmetries, you can actually see, obviously, they should have had the same amount. So the way to do it is that, notice at the beginning, the two volumes of green and white are equal. At the end, you have mixed them. But the total volumes are exactly the same as before. Right?
Yes.
So whatever is in green, there's some extra white in it, and whatever is in the white, there's some extra green in it, should be such that whatever is extra white in the green one must be exactly the same amount of the other one, so that if you switch it back, it will be the same amount you had before. In other words, let me illustrate this by this picture probably. Suppose you unmix it. Since the volumes are equal, you'll get some white on the top of the green and some green on top of the white, but you should be able to exchange them to bring them back to the same size. So clearly they must have had equal amounts. So symmetry in this case implies equality. And this is unintuitive, even though symmetry kind of cleans it up. In fact, to illustrate it even further, we can give an example of a deck of cards. Suppose you have two decks of cards, one black, one red, just like the two paints, and do the same game. In particular, take 10 cards. There are 10 red and 10 black cards, and then you take, let's say, 3 of the red ones and put it in the black, and then shuffle it. And then take 3 of these shuffled mixed ones and put it back into the red pile. So at the end and at the beginning, you have 10 cards in each. But the red one has some black and the black one has some red. The question is which one has a more mixture of the other one? And the answer is, of course, they have the same, namely, you have 10 altogether, so whatever is missing from the red must be over there, and vice versa, you could switch it back. So I hope that's clear. So this illustrates that thinking about it in a symmetric way and asking how much you had totally, conservation law tells you don't miss anything. You start with 10, you end up with 10. So whatever is missing from one goes to the other. That's called conservation law. So symmetry and conservation law in this case gives you the answer. Another example of the symmetries. Aristotle thought that heavier objects fall faster. If you ask most people, I think if you ask me, for example, before I had studied physics, whether heavier objects fall faster or lighter objects, I would have said heavier objects fall faster. And that's what also Aristotle thought. That's what he thought. But unfortunately, it's not true, or maybe it's fortunate, I don't know. So Galileo said, no, all objects fall at the same rate. How did he do it? He went and famously did the experiment on top of the Pisa Tower, where he dropped big stones and little stones, and he found that they fall both together, more or less at the same time. So he established it experimentally. But believe it or not, at that time, scientists did not believe too much in experimentation. So they asked him, oh, you mean you took this stone and you dropped them? You have to explain to me why they fall at the same rate. You cannot just do experiments. It was a very different methodology of science. They wanted him to, by pure thought, to explain why they fall at the same rate. And he found a very elegant argument based on symmetry. And this is what I want to show you. So he said, imagine you have 3 rocks, 3 bricks, of the same size and same shape, and you drop it at the same time from the same height. Of course, they fall at the same time. In this case, it's obvious based on symmetry. They're the same size. There's no difference between them. And since they're at the same height and you drop at the same time, there's no difference. They all fall at the same rate. Everybody said, yeah, we know that. So what? This is boring. Give us something useful. He said, well, what if you move the rocks around but keep the same height? Like bring this closer and then drop. They say, of course, we know that this is boring. You're just moving at the same height. We understand. It should fall at the same rate. No problem. Then he said, well, suppose you bring them and put 2 of them really so close that they're almost touching. In fact, let them touch. What about then? Doesn't matter if you move them closer or not. Together, doesn't matter. Again, fall at the same rate. But then he said, that's twice as big as the other one. So this is bigger and they fall at the same rate. So he convinced people, basically by tricking them gradually, to accept that, it must be true. So this is the way that by thinking cleanly about it, you convince and you cleanse your mind that heavier objects and lighter objects fall at the same rate. Why we get confused to think that way, that heavy objects fall faster than light objects, may be psychological. When you have a heavy stone in front of you and a light one, you pay attention to the heavy one. If it drops in your foot, for example, it really has consequences. So you pay attention to that. So somehow psychologically we think about the impact of the heavier one. And we confuse that with which one gets faster, which is not the case. Okay, so I talked about symmetries, but one of the most important principles in physics is not symmetry only, it's its breaking of a symmetry. Not having symmetry is even more interesting than having symmetry. But symmetries that are broken by themselves, and I will illustrate this by the next puzzle. Suppose we have 4 cities, A, B, and C, and D. There are 4 cities which lie on the corners of a square. These 4 cities are corners of a square, and we are trying to build a highway system connecting all these 4 cities together with the shortest total length of the highway. We don't care whether the cities can get directly from one to the other or not, as long as through this highway system, we can get from any city to any other city. Is that clear? Okay. Question is, what is the shortest highway system which does this? Now I'm going to show you some alternatives, and I want you to think which one is the one you think is the shortest. How many think this is the shortest?
Yes.
Okay. How many think this is the shortest? Okay. Well, if this is the shortest, we may as well take one of the lines off, because you can get from the other one with the other ones, you don't need that one. And in fact, you can move around one of the other lines, doesn't matter. It turns out this is the answer. Now, you see, this highway system looks like this. You bring them together first, and then you connect them with a 120-degree angle, and then go the other way. And then you said, what? Why? Why is this the shortest answer? What is strange about this? It is not symmetrical, you see? If you want to get from city A to city C versus going from city A to city B, it's faster, easier to get from A to C, but longer to get from A to B. Even though all 4 of them at the corner of a square, and the distance, physical distance between AB and AC are equal. Nevertheless, the highway system breaks the symmetry. This is called spontaneous symmetry breaking. That is, the shortest highway system is not necessarily symmetric anymore. You could start with a symmetric situation, but the answer is not symmetric. In fact, the early Greek philosophers encountered the same problem a couple thousand years ago. They already had discovered that Earth is round, very smart people, and they thought that Earth is at the center of the universe. You know, they have this round Earth, and it's the center of the universe. Nice. But then they were not understanding why is it not moving. You know, they were standing on the Earth. They didn't realize the Earth is moving. They thought it's just stationary, and they were trying to come up with reasons why doesn't the Earth move around. And they came up with an explanation. They said, you know, it is because of symmetry. So they were smart to know that symmetry may be an explanation. They said, well, suppose you have the Earth over there in the center of the universe, and suppose it starts moving. If it were to move, it has to pick a direction, and as soon as it moves in that direction, it has broken the symmetry. It used to be centered, there's no preferred direction, so picking a direction breaks that symmetry, and therefore they said, since it breaks that symmetry, it is not allowed. So therefore it won't move. Okay, that was their explanation. The Earth is stationary because moving any direction picks a direction, and that breaks the symmetry, therefore it doesn't want to do that. Okay, that was their explanation. This was the debate, but Aristotle very smartly disagreed with this reasoning. He said it's not a good reason. So how did he argue that? He said, suppose you have a perfectly symmetric situation, like a person in the middle of a circle. And suppose you spread food, loaves of bread around the circle. Okay, you're at the center of a circle, and there are loaves of bread around the circle around you. He asked, are you going to stand there forever because you're at the symmetric point? You don't want to break symmetry by going that way? Of course not, he argued. He argued that if you do that, what you're going to do is you're going to pick a direction, go and eat the loaf of bread. You don't care if it's not symmetric because you don't want to die out of hunger. So his point here was the most symmetric answer may not be the ideal answer. And in fact, that's what happened in that square example. The shortest highway system was not the symmetric one. The X would have been, for example, a symmetric one, but that was not the best one. Here the same. You have to break the symmetry, and you do break it. If we put any of you on the circle, I bet you will not stand there forever. You go and pick out the loaf of bread from one direction or the other. In fact, spontaneous symmetry breaking is imprinted on our heads. Look. If you look around you, in principle, there's a rotational symmetry horizontally. But you have eyes only in the front. You don't have eyes around your head. Right? Why is it that we don't have eyes around the head horizontally? We have broken the symmetry. In other words, the eyes break the symmetry. Our body knows about symmetry breaking already. Our eyes in the front. Why? Well, we need to get the food. we want to know where the food is and we go towards it. We don't need to know where everything is. We just go in that direction. So it's wasteful to have eyes all around us. Evolution has chosen the path that you need only the eye in the front. Breaking of the symmetry again. So even our body has signature of spontaneous symmetry breaking on us. So we all have broken the symmetry, and it is the way it is. Moreover, it was discovered already in particle physics that spontaneous symmetry breaking is the main reason we all have masses. Spontaneous symmetry breaking is the reason for what's called the Higgs particle, or some people call it the God particle, for things to get masses. And the way that appears is exactly like a situation that Aristotle was thinking about. You think about the hilltop, and that's like a potential where you can think about particles rolling, the field rolling, and it will roll instead of from the middle, it rolls down to the bottom of the hill. I don't know if you can see it down here. So the ball will come down here, and therefore you roll down. And you go from the symmetric point to this non-symmetric point because it's lower in height. And it turns out the mass of all the particles is proportional to how far away you are from the center. So we get mass because of this effect. Okay. So this was symmetry and symmetry breaking. And so my next topic is the unreasonable power of mathematics. Mathematics is unreasonably powerful. Now, you might think, yeah, because you have to learn differential equations, and yes, a little bit this and that, okay, higher dimensions. No. Mathematics is powerful, even the primary grade mathematics you all learn. And I'm going to give you an example of it. Primary grade mathematics. Nothing fancy. It's very powerful. So let me give you a question. Take the Earth and the equator. Consider the circle, which is in this case this white circle. Imagine that as the equator of the circle. Now open the equator. Open this and view it as a belt around the equator. So think about wrapping a belt around the equator and open it up. So this white thing on the thing is that belt. Okay, great. Now add 1 meter to it. So we added 1 meter here, this green thing. I don't know if you can see, there's too much light probably here. You added 1 meter to it, and then you wrap it around the Earth, the equator again, but now it doesn't wrap tightly, right? Because you have added 1 meter. The question is, how much does it rise? What is the rise here? What is x? Okay, we want to know what x is. Okay? Okay, let me ask the questions from everybody and see what you will say. How many people think it's more than 1 centimeter? Raise your hand. How many think it's more than 1 centimeter? How many think it's less than 1 centimeter? How many people don't know? Okay.
30 centimeters. 30 centimeters.
Okay, let's do the mathematics. First of all, before we say the answer, most people, when they think about this, including myself, before doing the calculation, you would think it's going to be like micron, tiny little things. Why? well, this Earth is huge. You're adding just a tiny meter to it, and you think it's going to rise a lot? No way. It's going to be just maybe an atom or something tiny bit. That's what the intuition said. It's my intuition said that. So let's see what the answer is. The answer is elementary mathematics, because you just need to know the relation between the radius of a circle and the circumference. If the radius is r, the circumference is 2 pi r. That's all we need to know. Okay? So we started with the radius of the Earth was r, the original radius, which is this red line filled here. It was r. So the circumference originally is 2 pi r. You add 1 meter, that's plus 1. And you think about it as 2 pi r, 2 pi times the new radius, which is r plus x. So you just say 2 pi r plus 1 is 2 pi r plus x. And if you multiply it out, you have 2 pi r plus 2 pi x. So 2 pi r cancels from the left and the right, if you recall your math from the beginnings. You see 2 pi x is 1, and you realize that x is 1 over 2 pi, which is about 0.16 meters, or about 16 centimeters. Okay? 16 centimeters. That's huge. Okay. So this shows, this is not fancy math, right? This is simple math, but it has unexpected consequences. Now, I was doing this in my class, and giving this puzzle to my class, and I said, did you all get this answer? And then they checked it. Someone says, no. One of the math people said, no, I got a different answer. And I said, what answer you got? I said, what did you do? He said, well, I didn't assume that they have to be rising equally on all directions. You can pull one side, right? You can also pull one side. What if you pull one side, how much does it come that way? How much? How many think it's going to be?
1 meter.
Half a meter? 1 meter? You added 1 meter. If you pull it up, it's 1 meter? Half a meter? 1 meter? Okay. The answer turns out to be 121 meters. Okay? Now, totally unexpected, right? You add 1 meter, you put it one way, like here, and it lifts 121 meters. Very unintuitive. How do you check this? You do math. This one is a little bit more than primary grade math. You need a little calculus around here, so I won't bother deriving for you, but it's true. 120 meters. And that was the answer that my student had gotten, and it's correct. 121 meters. So mathematics can have unintuitive results from physics side. This is quite, relatively speaking, simple math, but the answers are unintuitive. Now, a lot of the ideas in physical principles are based on what we call continuity. Continuity means things don't jump around, right? If the temperature now is like 15 degrees, in an hour it's not going to be 100 degrees. It's going to be maybe 16 degrees, maybe 14 degrees. Well, unless you live in Boston where I live, where it could jump that much. But more or less, I don't know how the weather is here, but usually it's crazy too. Okay, let's go somewhere else and assume it's continuous and slow. Okay, so now you know what continuity means, right? You have an expectation things don't jump around, just gradually change and so on. Okay. It turns out that this idea, the continuity, is a very powerful principle about physical laws. All the physical principles are based on principle of continuity. Nothing jumps around. Okay? So now here I'll give you the following puzzle. Again, let's go back to the Earth. I love Earth. And there's the equator again. And what we're going to do now is that we're going to measure the temperature on the equator. Of course, the temperature on the equator do not have to be all the same value. There will be different values depending where you are on the equator, right? So you measure the temperatures, and then you ask the following questions. Could it be that two opposite points on the equator, opposite relative to the center of the Earth, could they have exactly the same temperature? Exactly the same temperature?
Yes.
Well, of course, if the temperature is constant, of course there would be. The question is, if you take a random continuous temperature, would there necessarily be 2 points which have the same temperature? That's the question.
Not necessarily.
How many think necessarily there is going to be 2 points with the same temperature? How many don't think that's necessary, that there may be no such 2 points? Okay, majority is the way that most people think, so that's correct. I mean, that's wrong. I mean, sorry. So that's the way most people think, and that's the way I would have probably thought also. It turns out that no matter what, there always are 2 points on the equator opposite relative to the center of the Earth, which have exactly the same temperature.
At the same time?
At the same time.
No.
Yeah. Now, amazing, right? Now, it may be at a different time, there may be different pairs, but at every time, there are at least 2 points with exactly the same temperature opposite relative to the center of the Earth.
How do you prove that?
Easy. Let's see how it goes. Look at the temperature on opposite points. And suppose they are not equal, right? Then one of them is bigger than the other, right? If they are not equal. So let's take the difference of the temperature. Let's take the difference of temperature here minus the temperature here. It will be a positive number, right? Suppose we take the temperature over here and take their difference. Is that going to be positive or not? Well, if it's close enough to here, it's going to be positive because continuity. It's not going to jump around, right? So a little bit close to here is still going to be positive and so on. How about over here? If you get all the way down to here, the temperature here minus here, we know it's negative. Because we know this was higher than this. So the difference of temperature goes from a positive number here to a minus number here. Positive numbers cannot go to negative numbers without crossing 0 because of continuity. Some point it has to cross 0. Wherever it crosses 0, that temperature means the other side is the same temperature. Is that clear? That's the principle of continuity. So, in other words, you define a function which is the difference of those temperatures, and you know that if you go to the opposite point, that difference goes to the minus sign because you're just reversing the order of which one you're talking about. And so if you draw the path of the function, you go from a positive number to a negative number, it has to cross 0 somewhere, and where it crosses 0, the temperatures are equal. Power of continuity.
But is it because you assume that you have the same distribution of temperature around you?
Not distribution, continuous. I didn't assume it's anything other than it's continuous. The distribution is not I didn't assume anything about temperature, other than that it doesn't vary, it doesn't jump around. That's all. So again, I will say once again, if the temperature over here minus here is positive, if you look at the difference of the temperature as you go around the equators, it varies gradually, it doesn't jump. So you start from a positive difference, and all the way down when you go to the other side, it's negative because it's the other opposite way. So you go from a positive number to a negative number, so there must be 0 somewhere.
They should be continuous but not the same rate.
Right, but the point is that at that point where it is 0, it doesn't say in the middle you get 0, there's some place it's 0. So this shows continuity can have such a powerful implication. Now, in fact, if you open up your TV and tune up to the news tonight, you might hear somebody said, it was amazing. Today, at every moment in time, there were 2 points opposite to each other on the Earth, not necessarily on the equator, opposite in the sense that opposite across the center of the Earth, where they had the exact temperature and pressure. Not just the temperature and the pressures were equal. It was quite remarkable that this was observed, and at different times there were different points. So you would have a situation like this. The temperatures and pressures opposite points are equal, and this turns out again to follow by continuity. No other things. So again, it's the power of a mathematical idea of continuity, which happens to be the feature of physical principles. So without knowing details about the physical laws, just some bare bones of the mathematics of it, like continuity, you can deduce facts like this. Temperature and pressure are equal. So continuity is a very powerful principle. Now, this is another example of continuity, but this is going to be a little bit more abstract. So it might challenge a little bit in this general talk, but I will nevertheless try. So if you don't quite catch this puzzle or things, okay, this is a little bit more complicated example, but let me say it anyhow. So what is gravitational lensing? You see, Einstein's theory says that light goes over the shortest path. But it turns out that the space is curved, as we said in the context of Einstein's theory. So what is a straight line in a curved space might look a little curvy. And therefore, it could be that if you have a star here, the light that is going to you, which goes in a curvy path, might get one way, or another one could get different path. So you could get more than one light ray coming to you from this light source, because it could go curved. It's not just one straight line, it could be multiple lines that get to you. And in this way, this phenomenon is called gravitational lensing. That is, you can, just like lens bends the light, the gravity also bends the light, and you can see different images. The number of images might be different. Like this, the light. So you could be here on the Earth, and you have that galaxy, and you can get multiple light rays that get to you. And you get multiple images. In fact, if you look at this sort of galaxy, you actually have a few repetitions of the same object. You might think these are different objects, but actually, it turns out that is not the case. What you are seeing in the sky in this case is actually all the blue ones are the same quasar, and all the orange ones are the same galaxy. So here you are seeing apparently 3 different galaxies, but they are not different, they are the same. It's the same galaxy, but the light gets you from 3 different paths, and you think there are 3 of them. And that blue ones over there, you might think that there are 5 objects, but they are actually the same object. Remarkable. You get images 3, 5, etc. Of course, if there was no gravity, if there was nothing in between, you just get 1 image, right? The usual one is 1. Here you see also 3 and 5.
How could they find out that they are the same?
They studied the spectrum of the light and different features, and they cannot prove it, but it's good evidence that they look like they are the same. Too much similarities in terms of the patterns. It turns out the number of images you get, the number of gravitational images you get, is always odd. It's either 1, 3, 5, 7, or something like that. But not 2, 4, or 6, or something like that. Now, of course, you can do one thing. You can block the light. And so if you have, for example, 3 images, 3 lights come towards you, you can just, some naughty kid might block one of the lights, and you might just get two images. I'm not talking about that. So let's assume no light gets blocked. If no lights get blocked, you always get odd number of images, 1, 3, 5, etc. And this follows from Einstein's theory of relativity. I'm going to show it to you. Now, it might be a little bit daunting to actually use Einstein's equation in this short time we have, but it turns out that the idea for it does not delve too much on details of Einstein's theory, except that it's continuous. So it's basically the idea of continuity of Einstein's equation implies you always get 1, 3, 5, etc. images. So I'll try to explain how that comes about.
Sorry, is this capture over time or at the same time?
At the same time. So 3 images or 5 images I was showing you you might go and take a picture of the sky with these powerful telescopes, and you see, oh, there are 3 of these are the same, 5 are the same. Yeah, same time.
Isn't that evidence of dark matter?
Sorry?
Isn't that evidence for dark matter?
Not necessarily, even though dark matter can bend things. Dark matter could have helped in bending, but ordinary galaxies also can bend. So that's not necessarily a proof of dark matter. So here is an example. You have a light source like a sun or a star. Here I have a red picture for that, and this is our Earth. You get a light ray coming to you. But imagine the following. Take a sphere around the star, and take a sphere around, again, whose center is the star, but kind of passes through the Earth. So imagine this huge sphere centered at the star that passes through Earth. If you can imagine this huge sphere. We're not going to build it or anything, just imagine it, so no problem. So we have this huge sphere whose center is the star, which passes through the Earth. And then there's a little sphere which is around the star. Now, if you look at the light ray, each light ray comes and hits one of these points, and it also comes and hits a point over here. So you get what we call a map between this sphere to this sphere. Basically, you just take each point here to some point over here. That's called a map in mathematics language. So this is what is called a two-sphere, S2. This is a two-dimensional sphere, and you get a map basically by looking at where the light rays will go, which point goes to which point. You get a map from one sphere to the other sphere. If there was no matter in between, the light rays go straight. And when they go straight, it's clear that each point goes to the corresponding point, obviously, right? It's a very simple straight map, very simple. The same point goes to the same point on the other one. In this case, if we just had this one, the number of images is 1, right? If you're over here, and if you're looking at the star here, there's exactly one path, one light that gets to you, and that's one image. Okay? So if there's no matter, this is the map. But the degree of a map is defined as the net number of pre-images. How many given different light rays can you get to come to the same point? It turns out in mathematics, the number of pre-images of a given point, counted with some plus and minus signs, which takes into account whether the map is oriented or inverted, does not change because of continuity. So if you start with any number, and if you change these gradually, it doesn't change. So the net number does not change. To begin with, when there was no matter, the number was 1. This was just a straight map. And if you put the matter in between, the map might change, and you can kind of visualize it like this kind of a picture where the geometry of the sphere around the star could be viewed as changing. So the number of would-be straight lines, here you have only one straight line hitting it, but here this light that gets to you will cross the sphere here at different number of points. So let's see how many points you get at different points in the Earth. So here, for example, you just get 1. But over further down, if you were somewhere else, like here, you will get 3. And further down, you will get like 5. So the number of typical images will always pair up. And the point is that each time you go through one of these things, you just jump by 2 at a time. And the direction of going back and forth changes because you're doing plus and minus, depends on the orientation. So half of the images are inverted. So this is a slightly more advanced application of continuity, but it is basically shows that the ideas are not too complicated to give you such results. I could give you another example of a mathematical abstraction. So this is called the ant experiment. We have 4 ants on a plane, okay? And they are moving at a constant velocity. Not the same speed, but constant. They're not going fast or slow. They are keeping their pace, but in different directions. So these 4 ants are going in different directions with different speeds, but each one has a constant speed, okay? Now, suppose we know that out of these 4 ants, all pairs cross, not only their paths cross, but they actually cross. They get to the same crossing point at the same time. Suppose we know this for all pairs of ants except the very last pair. So the question is whether also the last pair should also cross at the same time. In other words, imagine these 4 ants. So you see they cross at the same place at the same time, and this one, and that one, and that one. The question is, and also this one, the question is these last 2, will they also cross or not? Do they have to cross at the same point at the same time or not? Will they collide? How many things that they necessarily have to collide? How many things they don't necessarily have to collide? Okay, so the majority is usually wrong, so therefore, they actually will collide, surprisingly enough. Now, the fact that their paths crosses is clear because they are not parallel. But the question is whether they actually pass through the same point at the same time. That's not as obvious. Now, the way the mathematical abstraction helps to solve this puzzle is to bring one more dimension. You go from two-dimensional plane to space and time. To space and a time. It turns out space-time perspective solves the problem. So what do I mean by that? Well, imagine a vertical axis which is your time axis. So at every time you see where the ant is, I'll put the point there. So if your ant is going, let's say, this way, just imagine you say, okay, the time is higher, 1 second later. So this later here, you put the ant here at the next layer, and so on. So you can view and draw a line where the ant is at each point in time. So think about as the vertical axis as a time axis. So saying that the ant is going at a constant velocity means that the path that the ant takes is a straight line. So you have straight lines that are going. So what we have is 4 straight lines in 3-dimensional space, 2 space and 1 time. So you have 4 lines, they cross pairwise. That's what it means to pass from the same point at the same time. That's what that means. If you have 4 lines which cross pairwise, you can show if all of them except one pair cross, the last pair also have to cross. Just by Euclidean geometry, simple properties of planes and lines. And so you can see it in this picture. So you can lift the dimensions and to view it as a time axis. So the ants are going on straight lines, that's your time axis. And so when they cross here, there's a plane they form here. And when they cross here, these two are the plane. Therefore, these both are on the same plane. The green and the yellow are the same plane. And therefore, they are on the same plane, they will cross. So just by Euclidean geometry, you just deduce they have to cross. You don't need any fancy computation. So this is the power of abstraction. What was the abstraction here? We went from 2 space to 2 space and time. Time became a dimension, just like the other axis. Just like Einstein's theory says time is also a new direction, new spatial dimension. A kind of a dimension like space. So now I come to duality. Duality is one of the most important principles we have discovered in string theory. It basically tells you that sometimes things which don't look like similar to each other are actually the same. That it kind of confuses you. In other words, 2 seemingly different systems can nevertheless be identical. It's like having a dark night and a white day and saying they are the same. Kind of you say, wait, night and day can't be the same and so on. But they have identical properties sometimes. And it's actually, it's a little bit like this drawing of Escher. You see, like, you have, on the left you have the day, and the right you have the night. And you gradually can go, morph the day to become the night. The sky, which is white, becomes the dark sky. And these birds, which are, flying on a blackbird, become the white bird. But in a very non-trivial way. You see, the black birds on the left are becoming the sky on the right. And the white birds on the right are actually part of the left sky. But it's so seamlessly done that this duality, this kind of situation happens, and it kind of can confuse us, but they're kind of the same thing. And also, going up and down, the fields, the black and white fields become the black and white birds, or the black and white sky, in a very elegant symmetric situation. So this is kind of a situation we call duality symmetries in string theory. That's one of the most important principles we have discovered in string theory. So I will have a puzzle for that. Now, I love ants, so the next puzzle is also about ants. You take a meter stick, 1 meter long, and you put 20 ants on it. Okay? You can put them anywhere you want on this meter stick. But once you put them, you can only instruct them whether they go left or right. And they all go with the same speed. But you can instruct them, initially at least, whether they should go to the left or to the right. Fine. You put them there, you say go left, go right, and so on, all these ants. They start doing their thing. As soon as 2 ants come and collide, they just go the other way back. So as they go collide and they switch back to the direction, they go the other way. Is that clear? Okay. Now, you will win this game if you can design where to put the ants and which directions they should go, so that when I forgot to say, the meter stick is just 1 meter, of course, and after an ant gets to the end of the meter stick, it just falls down, okay? So after a while, all the ants will fall down. The question is, where can you put the ants and which direction should they go for you to get the last ants in the meter state last as long as possible? Is that clear, the question? So in other words, we want a situation like this. We have these ants going, and when they come together, they collide in reverse directions, and they fall off. When they go, of course, as you can see, they fall off. And the question is, where do you put them originally, and which direction they go to maximize the time the last ant is on the meter state? This looks like a tough one, right? Now, here it's difficult to ask a question from the audience, so I will actually give you the answer. This one you have already given me a lot of nice feedback, so this one I'll spare you. The answer is, well, first of all, the answer is that, who said I should color the ants this way? Have you seen green ants, or red ants, or purple ants? I haven't seen these kind of colors. I mostly see black ants, right? So let's look at the black ants. Do you see them colliding? But wait a second, are they colliding, bouncing back, or going through each other? Or is there any difference? Do you see? You couldn't tell if they are colliding and going back, or they're going crossing each other without doing anything, because who cares which ant is which, right? So you do a duality transformation, so to speak, that instead of thinking the ant bounces back, you can think the ant goes through each other. There's no difference in terms of the picture that I'm going to get. Therefore, all you have to do is to take one ant at the left end and say, go to the right. You don't care where else what the other ones are doing. And that's the best you can do. Is that clear? Power of duality symmetries. You can get confused with this, but duality kind of says, oh, changes their role. Instead of bouncing, you can think about them going through each other. Now, finally, this is my last puzzle. And I like this probably the most among them because it teaches you about science, how scientists do science. It tells you about the principles we do. Namely, it shows you first look at the phenomena. You want to answer a phenomena, you do first a few experiments. You form a hypothesis. You check a few experiments. You try to check your hypothesis. You try to find an explanation for why your hypothesis is working. You do further experiments. This is the scientific methodology, and if it's not working, you change your hypothesis. So let's see how this goes. In other words, one is examples. We do experiments. We formulate a general principle based on them, and then we come up with arguments why or how it works. Is that clear? That's a cartoon version of scientific process. So we want to do an experiment. All of you are part of this experiment. We're just going to do the experiment. We're going to build a theory together. Ready? Okay. This is the theory we want to build. We have a circle. Okay, a green circle. And what we'll do is we take 2 points on the circumference of the circle, these 2 yellow points. And we connect them together. Okay, wonderful. We need to get a line there. The question is, how many regions do we get inside the circle? 2, very good. Okay, we did our first experiment. We got 2 regions. In other words, what we have is 2 points leads to 2 regions. Is that clear? Okay, good. Next experiment. We take one more point, the blue point. And then we connect all the points together to lines. So now we have 3 lines. How many regions do we have now? 4. Very good. This experiment is going really fast. So we have 4 regions. So we have 3 points, gives you 4 regions. Excellent. We are doing our experiments, right? Let's do more experiments. Getting fun. Let's take 4 points. Do the same thing. Connect every point with every other point. We're just choosing random points. We're not choosing any special points. All the 4 points randomly chosen. We connect them. How many regions do we get? 8. You guys are great. Okay. You see how it's working, right? In other words, 4 points, 8 regions. Well, we can put a theory, but let's not do a theory. Let's do one more point. Let's do 5 points.
25.
What?
No.
How many do you think this is? 16. You guys are really good. 16. Okay. So 2 points, 2 regions. 3 points, 4 regions. 4 points, 8 regions. 5 points, 16 regions. Do you get the pattern? What is the pattern? It goes up by a factor of 2 each time you add 1 point. Is that clear? Now, can anyone explain to me why? We have to have a theory, we have to explain it. You can't just say it is the case. You have to come up with a good, remember Galileo? He kind of explained it, right? Okay, can anyone explain it? Okay, I will help you if you want. Okay.
Because every time you add a point, you divide the remaining areas by 2.
You would think exactly like, you add a point, it's either to the left or to the right when you draw a line. That's why it's a factor of 2. Okay, good. So let's do one more point, and so the next point is going to be 6 points. I should get how many? 30. 30. 31. Do I have made a mistake? Let's just check. Am I missing something here? I don't think so. The answer is 31. So what do we deduce? Our theory was wrong. Okay? Don't be too shocked. You see, we saw that pattern. It was beautifully going. We came up with a theory. We do more experiments. We explained it, and it doesn't work. We have to go back and figure out the correct theory. This was the wrong theory. Okay? We can be fooled. Experiments can fool us, as it fooled all of us now. The answer is 31. Now, you might be curious, what about if I have 7 points? It's not 64 anymore, right? It's 57. It's close. Not quite right. In fact, there's a formula for it. The formula is the number of regions is 1 plus n choose 2 plus n choose 4. For those of you who don't remember what n choose 2 and n choose 4 are, it's just some polynomial in n of degree 4, this whole expression. So it's n to the 4 plus whatever. Now, it stops here. If this went n choose 6, n choose 8, etc., then it would have been 2 to the power of n minus 1. The fact that it stops means it mimics 2 to the n minus 1 for n up to equal to 5. But then it stops. So it kind of, the formula is designed to fool us, to be almost power like factor of 2, but not quite. It doesn't quite work that way. So I hope I have conveyed the power of simple mathematical ideas in the context of physics. Even the most advanced ideas in string theory have simple mathematical underpinning, just like the puzzles we have discussed today. Thanks for listening to my talk. Conduct a session in the sense that I will try to direct whoever asks a question. Please feel free to ask any question. But my only request is speak your questions loudly so everybody can hear it, and make it kind of to the point and short so that we have time to get to everybody's questions. So let's start. Yes.
My brain is still working on the ends of this
Stick.
stick.
Yes.
I missed. Have you said where would you put those
Yes.
ends so that you maximize the time?
Yes. So let's say it again. So the problem was that the ants are going and they're bouncing when they collide. But suppose we say the ants don't bounce when they collide.
Oh, I
Suppose.
understand that part.
Okay, so we say, so the point was that whether we say they bounce or they don't bounce, they look the same. Do you agree?
Yeah.
Okay, so if they, so that means that you just have, you can imagine the ants are just going straight from one side to the other. So how can you make the ants last longest on the stick? Well, you put one at the very end and you tell them to go that way to the right. That's all you can do. That's it. That's correct. Yes?
Consider similar to the, for example, those examples, consider a graph y equal 1 over x, and consider the part that is for each node are equal to 1, and rotate it around the x-axis. The shape has a finite value, but has infinite surface. Is it just like those examples, or no? Is the problem we can measure?
No, that's a correct statement. You can have something which has finite volume or infinite area or whichever version that you have. So that does not have any problem. This is just a mathematical statement. There's no contradiction. Now, physically, to have a paint to do it, it has a size. So the idea of the idealization of physics by mathematical abstractions always breaks down somewhere. So that's why this is a mathematically correct idea, but it doesn't mean physically it has any significance. So I would say that's one of those questions. But some questions in mathematics are interesting, but do not necessarily imply anything deep about physics. This is one of them. Yes?
Do you believe in parallel universes?
Well, the definition of parallel universes has to be clarified. So one version is that at the time that we have this universe, there is some other universe which is happening very different from our universe. That could in principle be, but the only question is whether or not it has any interaction with our universe. If a parallel universe has no interaction with our universe, then there's no way of knowing, and who cares? In other words, you can say yes, it exists or doesn't, and since it has no impact on our universe, whether you say it does or does not exist has no implication whatsoever. However, it becomes a science question if you say there is a parallel universe and it has some impact in our universe. And then one has to talk about what kind of impact it might have. We do not know currently whether or not there are things like parallel universes which can have impact in our universe. The idea that there could be multiple types of universes with totally different properties is something that string theory naturally suggests. There's a landscape of all the different kinds of physics that we can get from string theory, depending on what are the shapes and the sizes of the extra dimensions in string theory. So for each shape or size and geometry and topology of these extra dimensions, you get a different kind of a universe, and you can think of each one of them as a universe in its own right. So in principle, we can have multitude of parallel universes happening. Whether or not it has an impact on one to the other, and in what form, nobody has really a good theory about them. Yes?
It said that string theory makes no testable predictions. When can we expect to see more?
Okay, so very good question. This question always comes, and I'm glad somebody brings it up. First of all,
Can you repeat the question?
the question is, string theory does not make a testable prediction. When can we test it? So the statement, I will modify the question a little bit. String theory does make testable predictions. It doesn't make testable predictions which are available to test with current technology, is the more accurate question. So then your question will be, when can our technology improve enough to see the grand structure of string theory? If I reformulate your question. And then that's a question to engineers. No, I'm just kidding. But yes, of course, in science we need to experiment something. And one of the shortcomings of string theory is that we don't have concrete experiments which can actually, give definitive proof that this is the correct theory. Of course, we don't prove things in physics. We just give more and more evidence. So there already is some evidence about string theory, which is one of the first examples of it is that if I let this go, it will drop. So there's gravity. String theory predicts gravity. It's the only theory that predicts gravity. It doesn't assume gravity, it predicts gravity. So there are some predictions, but one would like to have more detailed predictions and so on. And more detailed predictions is difficult to check in string theory because the size of the strings is 10 to the minus 33 centimeters or something like that. 10 to the minus 30 centimeters, just to give you a scale, I think I said it, a trillionth of the size of the atom or something like that. It's too tiny to see. It's too tiny to do experiments. However, there could be some predictions of string theory which have to do with cosmology. You see, the good thing about cosmology is that we came from a Big Bang, or maybe before it. Something was very small, and that has expanded. So maybe we are seeing in the sky evidences for what was there when it was really tiny. So maybe that has been magnified thanks to the cosmic lens, cosmic acceleration. In what sense can we see it? Maybe we can have predictions. Actually, it's interesting, as we speak, this theory, these kind of ideas are being discussed. Myself, very interested in that kind of idea. One kind of prediction these can make is the structure of dark energy. We have, 70% of the energy in the universe is what's called dark. And the question is whether this dark energy changes or not. Up to now, the belief is that this doesn't change. But string theory, some models in string theory seem to naturally predict it actually should change. and in particular it should decrease. Dark energy decreasing can be detected by experiments, and they're actually doing it now. In 4 or 5 years' time, we may know if it changes or not. So there are some hopes, but I wouldn't say we are sure about whether we will see them or not in our lifetime. But somehow, in some time, they should see it, otherwise it's not physics. Yes?
I'm decided if you believe Big Bang theory or not.
If I believe Big Bang theory, of course I believe Big Bang theory. So why do we say we believe it? First of all, I have to tell you what does the word belief mean in physics. Belief means do we have evidence for it? Nothing in science gets proven. It's not like mathematics. Even though there's a lot of relation with math, you don't prove anything in physics. You get evidence for physics. Big Bang, we have a huge amount of evidence for it. We know by the various observations that objects are getting farther from us. We see their galaxies. The farther they are, the faster they're going away from us. So you can extrapolate back. Where were they 1 billion years ago? 5 billion years ago? And you say, oh, they were coming closer together. And you say, how about 13 billion years ago? Did they come together almost at the same point? Well, we have evidence. That's an evidence. There are more evidences, like you can predict the abundances of light nuclei, like how much hydrogen do we have versus helium. You can measure them in the galaxies. Big Bang theory predicts a ratio which agrees with what you observe. Another example. The Big Bang, if you extrapolate back where the galaxies are when they were 14 billion years ago, you find they're at the same point. You say, aha, so the age of the universe should be something like 14 billion years. And then you go and measure the rocks and the Earth to see what's the age of those. If it's more than 13 billion years, it's a problem, right?
Where's the physical correspondence between these things? When I think of the space we live in, I think it's a real physical thing.
Yes.
But when I don't understand how you could conceptualize why would a higher dimension have any physical significance? And what is the basis for its physicality?
Okay, so you're not talking specifically about the question about gaps. You're not, right?
No, I'm just pointing out that philosophers would say, for instance, Kant said that there was a priori, we have to have 3 dimensions.
Right, okay, so I understand your question. So the question is, why talk about other dimensions? But come on, we see 3 dimensions. What am I talking about, he's asking. Is it this universe we are talking about or you're making up? Okay, that's a less polite version of that same question, but I think that's more or less the question. So let me actually try to give a reformulation of that example. So we do an experiment together, okay? Suppose you you're far from something and you see this one-dimensional line going. And somebody asks you, what is the dimension of that object over there? You say, come on, of course, it's one-dimensional, look. You get closer to it, you say, oh, maybe I wasn't right. It looks like it has a little bit thickness, maybe. And then if you go closer and closer and closer and closer, you might see, whoa, if you were like a little, I don't know, ant or something on this, you would say, wow, this is a huge circumference, and so it's like a hose and so on. So it's actually 2-dimensional. Okay, so now I come back to this. Is that line that we saw 1-dimensional or 2-dimensional? Well, you say, okay, it was 2-dimensional, you just didn't see the other side. But for all practical purposes, it behaves like 1-dimensional if you're far away, right? It is that sense that we say our universe could be 3-dimensional looking, but in reality it's these extra loop-like circumferences that's hard to detect. And they become important when you ask questions which are much smaller than what we have experimented on. So the answer to your question is the physical reality could have extra dimensions, but could effectively look 3-dimensional, just like the hose from far away or from a bigger object perspective looks 1-dimensional, can be really 2-dimensional. That's the sense. So there's only one reality. We are not saying there are multiple realities, but a single reality can have multiple different levels of approximation that they look like. 1 or 2 or 3, depends on how refined you ask the question.
But may I add something to that?
Yes?
When Einstein formulated his theory of general relativity, it's based on a well-established principle of equivalence. And from that, you can derive all these amazing things.
Yes.
But in string theory and other abstractions, they're mathematical games. So there's no physical principle that people are starting with right now to try to devise a new theory. Which is
Why do you say it's mathematical games? How much do you know about string theory?
Well, maybe nothing compared
So,
to
let me, I want to debate. I wouldn't call it mathematical games. I think people who are against string theory might say something like that. But I think the statement is that you have to say what's the basis of the theory. So let me explain to you why we think string theory is correct. There is gravity, that we know. There is quantum mechanics, that we also know. And we know that when there are forces, in most of the cases in physics we're aware of, what mediates a force is a particle. Like electric and magnetic forces are mediated by a particle called photon. All the forces are mediated by a force. So gravity will have a particle called graviton that mediates it. So when physicists try to write physical theories describing gravitational forces by exchange of gravitons, they found that the mathematics gives infinities. It did not make sense. So the problem was the traditional way that the photon gives forces between electrons does not work for graviton giving forces between massive electrons. What was the correct theory? There is no convincing evidence of what the correct theory is except for string theory, where it combines quantum mechanics with gravity. That is a strong evidence for string theory. There's no other complete theory, complete or not, maybe I should say complete, there's no other well-formed theory like string theory which does that. Having said that, I have to say there are many questions in string theory we don't really understand. For example, we do not know the analog of Maxwell's equations for string theory. I cannot tell you this is the theory and derive all the consequences. We do not know it that well. But we have found so much evidence for it. To say it's just mathematical games is not fair to it. They are based on physical principles that we know about and trying to put them in one framework. And another fact is, when people try to describe, when people discovered string theory, they originally didn't even know there's gravity in it. They later discovered gravity was part of it. It wasn't like made up to give gravity. It was far more elegant. So some people said that string theory is too smart for human beings, that we were somehow lucky that we coincidentally found it. It's in some sense beyond. It's not like, oh, let me come up with a theory to do this. It's kind of a little bit smarter than us. But that's precisely why we haven't developed it as much as we need to have it at the stage where we say, oh, this is completely understood. It's not completely understood. After 50 years, it's still being worked out. Mathematicians are very interested in physics of string theory because it has a very rich mathematical structure. Some people confuse this by saying, oh, physics, string theory is just mathematics. No. It is so rich that mathematicians are interested in it. Just like Einstein's theory is very rich geometrically. Riemannian geometry is very rich. It is not against Einstein's theory to say it's mathematically rich. String theory is mathematically rich and it has caused a lot of interest by mathematicians to study it. I'll just give you one example to say how interesting it is. So if you try to measure the mass of the electron in string theory, you have to know how many spheres fit in these extra dimensions. We have to count. And we have to count whether it's wrapping once around it, how many spheres can wrap once around it, how many spheres can wrap twice around it, and so on. It is very difficult to do these calculations in these 6 extra dimensions. So physicists were struggling to come up with computations, but then they found the symmetry by the duality symmetries I told you about, which mapped this question to a very simple integral. So they calculated how many spheres wrapped once there are, how many wrapped twice there are, and so on. They found that for spheres wrapped once in a particular space, there are 2,875. And for wrapping twice, there was 200-something thousand. Okay, huge numbers. Mathematicians had only calculated how many spheres are there with wrapping once or twice. And they did not know the answer for wrapping 3 times or 4 times or 5 times or any number of other times. But physicists using string theory computed all of them. Mathematicians were skeptical because these are very difficult mathematics questions. And these string theorists who have no idea about mathematics are making such bizarre predictions. So mathematicians went about trying to actually compute them, to see if it's correct what physicists are saying. To calculate the 3rd degree, the first one that mathematicians had not computed, was very difficult. So a few mathematicians started doing it. This was in late 1980s. Or maybe 1990, late 1980s. And then they started doing the calculation, and they found that the numbers physicists were getting is actually not right. So they said, well, thank you, physicists, but your number, the third number is not right. The first two are correct, but the third one is wrong. Okay? Now, what's the lesson? Well, a few weeks later, they came back, sorry, our computer had an error code. Your answer is correct after all. And so this is mathematicians trying to prove it or disprove it. After that, they said, we believe all the rest of your numbers. Okay, do we have a proof string theory is correct or not? Well, this is the kind of evidence that it is rich mathematically. It doesn't prove string theory, it's the theory of nature. It proves that it's definitely rich mathematically, and mathematicians are very interested. It is hard to believe that such a rich theory, that has such a rich mathematics, is not good for something. So we believe that's one of the other reasons that people are really studying string theory.
Thank you very much.
You're welcome.
Speaking of rich mathematics, Frege once said that every mathematician is at least 50% philosopher, and every philosopher is 50% mathematician. So in string theory, which depends so heavily on mathematics.
But think about this as a periodic box. What do I mean by that? I mean, suppose as I go that way through this wall, I come back from that side. Just imagine, like a video game, if you want for a moment. Suppose if I go up here, I come down from up here. So it's like a three-dimensional, what we call three-dimensional torus. So this is a universe, a three-dimensional universe. Just imagine. So you cannot exit. When you go that way, you come back this way, and so on. Is that clear? Okay. Now imagine squeezing this box to tinier and tinier space. It's not very comfortable, okay? But just imagine squeezing and making this wall and all the sides coming together. Imagine it's like 10 to the minus 30 centimeters. Continue squeezing it. Well, you can say, I can squeeze it any much I want. It turns out that if you squeeze it past like 10 to the minus 30 centimeters, it behaves as if it's expanding. That is, the universe of the size 10 to the minus 50 centimeters is the same as 10 to the minus 10 centimeters, or 10 to the minus, in other words, the other way. So what behaves like squeezing is like expanding again. So this is totally bizarre. This is part of the duality symmetries. The small and the large become equivalent. Very bizarre. Radius and inverse of the radius are the same if you pass through some particular value of radius. So there are many examples like this. So string theory is full of it, and it's called duality symmetries. That was one of the examples that I said about the ants. Came from these duality symmetries. By the way, I should say that almost none of these puzzles I presented today were my own. Many of them I learned from here and there. A few of them I learned from my own children, who were coming back from their primary grade school homework saying, Dad, they have this problem for us. And I looked at them, I couldn't solve them. Of course, Google is very useful in this case.
Regarding dark matter, I've got again a couple of questions. First, we know that dark matter doesn't have electromagnetic interaction, and it is why we cannot see. Yeah. And the other thing is that, for example, it does have gravitational interaction. So what about the other two forces, other two attractions? For example, weak, electro-weak, for example? Or
no, we think that the dark matter does not have any of those interactions other than gravity with us.
Okay. Doesn't have for the
no, nothing that we can see.
Do we have anything at all about the type of particles of dark matter? For example, we are vector particles or tensor particles.
We don't know much about them. People have many theories, and people are contemplating what they are. So he's referring to the fact, so some of you may not know, that 95% of the matter and energy in the universe is in a form we don't know what they are. It's just mysterious. Only 5% is what we know, proton and this and that. 95% is unknown. We are a terrible minority in this universe, okay? Let's face it. We have to be kind to minorities. We are ourselves a huge minority. 5% of the matter and energy of the universe is what we are. The majority is something else. And we don't know much about it. 70% of it is energy, pure energy, and 25% of it is what's called dark matter. So these two things we don't know much about, and people have various theories what they are. We don't have a clear idea. Yes?
So the string theory described from the time of Galileo upward.
Yes.
Apparently face inconsistencies, and we added additional dimensions till we, I think, reached the M theory that you said 10 or 11 dimensions. Is it right now at the stage that we say it is consistent?
String theory did not change too much, actually. So string theory, Galileo and Klein did not start it. It started in the late 1960s. Some guy called Veneziano wrote a formula, said this is a nice formula. similar to this question about this elegant mathematics. He was trying to describe some physical scattering process. And then a few years later, people figured that, oh, if you have vibrating strings, it behaves like the formula that was written down. And so then they studied that theory. Within a few years, they discovered it has to be 10 dimensions, 9 space and 1 dimensions. That was like in mid-70s, 1970s. The story hasn't changed since then. Now, let me say it more clearly then. What we discovered is that the 9 macroscopic space, can have one extra circle dimension, and in fact it does have extra circle dimension, just like the example of the hose I told you about. In other words, string theory itself behaves as if it's 9 spatial dimension, but if you probe it down to deeper, shorter distances, it reveals an extra dimension. The 10th dimension, so it becomes 11-dimensional. So it's not like you're changing the theory. It's like saying, oh, is that line 1-dimensional or 2-dimensional? The theory is not changing. That hose is that hose. So you can learn more about it, you can describe it more accurately. That's all.
And does it now actually reaches that holy grail of the unified theory?
It always, string theory, one of the amazing things is that all the particles is represented by just one string. In different vibrational modes and different structures they have, give you different particles. So all the particles and all the forces come from string. So it's actually beautifully unifying. So this thing about philosophy that somebody asked, about mathematicians and philosophers is more or less 50% one or the other. I would add to it also physicists. Physicists are, in fact, both mathematicians and philosophers at the same time. And in fact, I would add to that there has been some culture of being against philosophy in physics, and I don't quite understand why. There's this anti-philosophical tilt among many scientists, and I don't really know why they find that way. So occasionally they put down philosophers, saying, oh yeah, this discussion is getting useless, become philosophical, let's put it aside. And I think that's not accurate in terms of what they're actually thinking. I think many scientists, first-rate scientists, are actually deep philosophers, whether they admit it or not. Yes?
In string theory, is it the strings or the fields which is fundamental?
Strings and fields are the same. Strings, so there's the string field, and strings is the manifestation of the string field, just like the usual, for example, there's a field for photon, is electric and magnetic fields. Just the relation between electric magnetic fields and a photon is like string field and string. So it's more or less the same object. It's just different description.
Yeah, but so it is not somewhat like the present field theory, which tries to represent particle as a perturbation in the field.
Well, string is an excitation as we can think of without the field. That's the same. That's the same thing as we say about the photon. It's the same thing. Yes?
Does string theory predict anti-gravity as well?
There are versions of string theory which could have a negative, what we call negative brane. And these negative branes will have what we could call anti-gravity. But these theories have problem with unitarity. Unitarity means the probability that something happens is exactly 1. May not work in these theories. So you could have some exotic versions of theory which could have that. But this is not believed to be the case for typical string theory. No. Yes?
A reasonable answer for the information lost in black holes in Hawking theory, and in continuation of that, the observation of gravitational waves. So, what is the possible contribution of gravitational waves possible in string theory or in that problem of loss?
Okay. The second question, the gravitational waves in string theory or regular Einstein series is one and the same. So that doesn't change. No change in that. As far as the information puzzle, one of the things we have discovered in the context of string theory is a principle called holography, which means that in some contexts the space, the gravity behaves as if it's one lower dimensional object. And in that context, like in our universe we have 3 space and 1 time, in some way it behaves like actually 2 space, not higher, but 2 space and 1 time. And the information about what's inside is encoded on the boundary of the space. So that's called holography, like a hologram. So the universe is kind of like a hologram in 2 dimensions rather than 3 dimensions. And in those contexts, the information puzzle of black holes is believed to be resolved in some form, because we know that the physics on that hologram is very regular and we understand it. So the belief is that in some way it has to be resolved, but the detailed mechanism is still being worked out. Yes?
You mentioned all the particles are string, and the difference between particles is different vibration. Any idea how this happens?
We understand how this happens in the context of string theory, yes. So, you mean how the different
vibration happens? I mean, what is the cause?
Well, when I said vibration, why the string vibrates? Well, string has a tension, so it vibrates. But when I said vibration, I was being a little bit, speaking a little loosely. So, string can have different modes. Vibration is one of them. It could also have the following property. You see, I told you that there's these extra dimensions. So a string can wrap around them and vibrate and this and that. So it turns out like if you have a circle in the extra dimension, and if your circle wraps around it once, from the viewpoint of the lower dimensional theory, which is free space, it looks like a +1 charged particle. If it wraps the other way, it's minus charged particle. If it wraps twice, it's twice the charged particle. So properties of particles and
a reasonable answer for the information lost in black holes in Hawking theory, and in continuation of that, the observation of gravitational waves. So, what is the possible contribution of gravitational waves possible in string theory or in that problem of
okay. The second question, the gravitational waves in string theory or regular Einstein series is one and the same. So that doesn't change. No change in that. As far as the information puzzle, one of the things we have discovered in the context of string theory is a principle called holography, which means that in some contexts the space, the gravity behaves as if it's one lower dimensional object. And in that context, like in our universe we have 3 space and 1 time, in some way it behaves like actually 2 space, not higher, but 2 space and 1 time. And the information about what's inside is encoded on the boundary of the space. So that's called holography, like a hologram. So the universe is kind of like a hologram in 2 dimensions rather than 3 dimensions. And in those contexts, the information puzzle of black holes is believed to be resolved in some form, because we know that the physics on that hologram is very regular and we understand it. So the belief is that in some way it has to be resolved, but the detailed mechanism is still being worked out. Yes?
You mentioned all the particles are string, and the difference between particles is different vibration. Any idea how this happens?
We understand how this happens in the context of string theory, yes. So, you mean how the different
vibration happens? I mean, what is the cause?
Well, when I said vibration, why the string vibrates? Well, string has a tension, so it vibrates. But when I said vibration, I was being a little bit, speaking a little loosely. So, string can have different modes. Vibration is one of them. It could also have the following property. You see, I told you that there's these extra dimensions. So a string can wrap around them and vibrate and this and that. So it turns out like if you have a circle in the extra dimension, and if your circle wraps around it once, from the viewpoint of the lower dimensional theory, which is free space, it looks like a +1 charged particle. If it wraps the other way, it's minus charged particle. If it wraps twice, it's twice the charged particle. So properties of particles and so on gets translated to geometrical properties of strings. So when I say all particles are the same, in string theory means, well, it could have strings wrapping this way or the other way or oscillating this way or that way. And so it unifies all these aspects into one object. Yes?
The new dimensions that you talked about, the 6, are they mathematically equivalent to the 3?
Yes, there's no difference. In fact, it is in every aspect. In fact, it's just like symmetry breaking. You see, I told you that if you have a plane, you can rotate it this way. So if you have a line, and if you have a circle around it, this circle and the line look very different. But if you make it a bigger and bigger and bigger circumference, it's like a hose getting bigger and fatter, and you open it up, it's almost like a plane, then it's symmetric. There's no difference between the circumference. So what you do is you break the symmetry between this direction and that direction when it's small. But when it's big, there's no difference. So it's like spontaneous symmetry breaking. So different dimensions, 6 and 3, one becomes small compared to the other, is like spontaneous symmetry breaking. Yes?
How do we arrive at the size of these particles? In your slide you had a figure of 1/3 of 1 trillion, the size of the particles of this.
How do we come about with it?
Yes, how do we arrive?
Yes, so in physics there are fundamental units of length, time, and mass. How do you get them? From Newton's constant, from speed of light, and from quantum mechanical constant called Planck constant. From these constants we can find out what's the fundamental unit of space. It turns out the fundamental unit of space, smaller than which it doesn't exist, is 10 to the minus 33 centimeters. That's how we got that number. And what that means is that the space smaller than that is like a boiling geometry. It's not smooth. So the meaning of space does not exist if you go too far down in dimension. So what you see like a nice, smooth thing is an approximation. If you zoom in, it will look very, very chaotic. It's very chaotic if you go down to a scale much smaller than the trillionth and the trillionth of the size of the atom.
This obviously has not been tested.
It has not been tested, it's theoretical. Yes, correct.
So how do we arrive at this idea that below that
We do computations.
Okay.
We have evidence why that happens, but the details of what would it look like if we did the experiment is not done.
Is that what you call a quantum field?
Quantum foam. Quantum gravitational foam is what's called. Yes.
There's a lot of talk about string theory being the only game in town when it comes to unification. Is there any competing theory which
Yes, well, people do talk about loop quantum gravity a little bit. I would say it's not at the same stage of advancement of string theory. It's like, it is a bunch of ideas that has been put forward, far more primitive. I wouldn't say it's at the scale we can compare to string theory, despite what some proponents might wish. Yes, exactly. Who's not too far from here. Yes. 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 Go on.
A crazy question.
Okay. Every question is good, which is crazy. Yes.
Can you extrapolate this string theory into human relations?
Oh yes. Oh, I know what you mean. In what sense do you mean? I'm not sure.
I don't know. I'm just wondering if there is any application of this theory.
Oh, I see.
Just
Okay, I hope so. Maybe I haven't thought about it too much. So I think that many odd models in mathematics have applications in many areas. So I could imagine that you can take some of the ideas of string theory and apply it to human psychology or human relations and so on. I don't think anybody has done it, but I don't see why not. Yes?
Does each string have an infinite number of configurations, or is it finite? Is it continuous?
So, good question. So we think that it has naively infinite. But if you try to excite higher and higher energies, it might actually lose its meaning. In other words, after a while, it becomes higher and more unstable. So formally yes, but not in reality. So it will break up to pieces and bits.
It's a crazy question. We have, for example, theories that why, for example, when photon stops and changes to, for example, a particle and antiparticle with different spins and different charges and this kind of thing, and vice versa, when, for example, particle and antiparticle collide photons. But do we have any, for example, theory that shows the mechanism? What happens that, for example, this change happens?
Yes, yes.
What is the connected? So what is
that was the pair of pants I drew.
Pardon?
Pair of pants.
Pair of pants.
Yeah.
Is that theory?
No, I was drawing it in the top. You see, you remember the two strings came and joined? Right. That's also called a pair of pants. You see, it looks like a pair of pants. Now, you can think about this side of the pant as a photon, and then going down as the two particles you're talking about. So that's the process.
So does it connect, for example, the spin of the particles to the...
Yeah, you can show that. You can show it's perfectly consistent with the photon going to this pair and so on. So there's no problem with this. So those are the string diagrams and it unifies them. Yes, please.
Is the space continuous or discrete?
Well, this is related partly to the question about shortest distance in space. So the space smaller than 10 to the minus 33 centimeters or so, what's called the Planck length, is believed to be not to be describable by anything like either a point discrete or continuous. This is a completely bizarre object. Space is an approximate concept which is correct bigger than 10 to the minus 33 centimeters. So the statement of what is fundamentally a space is not understood. We only know that the notion of space only exists beyond a certain distance. After that, that notion breaks down, and we have to replace it by a different concept. So the notion of and this is one of the concepts of duality. The duality concept tells us sometimes there's no absolute meaning to some statement. So when you ask what is the real meaning of this, the answer depends on what's your question. If you ask one question, it looks like one reality. If you ask a different question, it's a completely different one, and yet they are both correct. Yet they're both correct. And that's kind of like the picture of Escher I was showing you. Is it dark? Oh yeah, look at that corner over there. Is it day? Oh yeah, look at the other corner, and so on. Are they the same universe? Yeah, look, it continues to go from one to the other. So depending on what kinds of question you ask, in string theory, it also is like that.
Can you say continuity and discreteness is duality?
Yes, it could be. But I wouldn't say continuous or discrete. I would say the notion of space changes from a continuous one to something bizarre like discrete one in some dual way. It's something like that. But I wouldn't say discrete in the usual sense like a lattice, but some form of a duality. Yes?
What powers these vibrating strings, and is it ever going to run out?
Power?
Yeah, where do they get their energy to do what they do?
Well, the energy depends on how much energy you give. So what the origin of the energy in the universe is and what's the entropy of the universe, where it comes from, we don't know, of course. But you know, the question is you're asking is a deeper question of where do you start from? But you can say if you start with this when this happens and so on. What's the origin of the universe and how the origin of the matter is and what's the entropy of the universe? Why the entropy of the universe is so big and why the energy is so much and so on. These are questions we don't have a deep understanding, of course. Yes?
So in that relation, is the energy per string subject to the law of thermodynamics?
Yes. You can have energy if you have the temperature.
So it may lose some of that vibration or the...
Well, it can go from one string to split to two strings, or they go from one vibrational mode to another, just like regular matter. There's nothing.
So is it possible that you think that this energy will die down at some point?
No. Energy is conserved.
No, I mean, all change to temperature. What I'm trying
Temperature
to
is energy.
No, I know, but the vibration on the string changes the vibration on the string to some other form of energy, which does not...
Well, you can only have, if everything is a string, it forms a different string, not...
Okay.
So then just ask him before, how much time do we have, Mr. Tabrizi? He's the boss here, we have to decide.
As much as you want.
Okay, so let's continue then. Let's see, who hasn't asked the question yet? You haven't asked it.
How do you explain the space curvature with
It turns out that string, when it moves, it creates a curvature around it. Just like any matter does. So string itself carries with it some mass. Or it's a layer of mass when it moves. And that causes the curvature to change. Yes?
People are talking about this energy level or energy of the string. Would they be discrete energy levels, so you can't lose energy until you jump to the next energy level below that?
Well,
or is it just like a...
Well, the rest masses are discrete.
Right.
In fact, the mass squared of strings are quantized, 1, 2, 3, 4, but it can move. So if you have some string of mass n and can go to the two lower masses and a movement, kinetic energy is continuous, so you can have so it cannot prevent from them happening. Yes?
Sir Isaac Newton was trying to use the Bible to map heaven and hell.
Yes.
Can the string theory predict the beginning of time?
Well, I do not know the connection with Newton. Newton was a very religious person. He was doing physics in order to prove the glory of God from his viewpoint. That's surprising to some, but actually he has written more about Christianity than about physics. Newton. So his motivation was very different from what we may think now. But the relation of that to your second question, I didn't quite understand. So
the second question was, can string theory predict the beginning of time?
Right now there are models what happens when you go back in time. And for example, this symmetry I told you that if something gets smaller and smaller, it gets bigger and bigger, could be saying, oh, so if you went back in the time, the universe gets smaller and smaller, and after some time, it actually is effectively getting bigger because small is equivalent to big. So that could be, there's no beginning in that context. It just goes to a different universe, a bigger universe in the past. So we don't have a proof of it, but that's a particular model that can work that way. Then just who hasn't asked? You haven't asked a question.
How well do we know string theory? How complete is string theory that we know of?
We know a lot about string theory by examples, like phenomena that we have discovered. Like I told you a few of them, like small and large are equivalent, or the properties of strings wrapping around circles, giving you charged particles. We have a lot of properties known about them. We know that they give you particle content like the ones we have seen, potentially, like quarks and electrons, photons, and all that can come from string theory. But we don't have a concrete thing like this is string theory as axiomatic A, B, C, and D. If these are satisfied, you have a string theory. We don't have such a formulation, and I don't know when we will get it. But we know a lot.
That goes time back and goes to zero, the size of the world. So does it have any conflict with uncertainty, for example? What can we say in terms of that?
Time doesn't go to zero. We don't know what happens before it. So there are different kinds of ideas about what is the origin of time, and people are still debating it. I don't think we are at the point where we say that time stops. Some ideas exist, like Hawking and Hartle had this idea that there's a universe which has no beginning, in the sense that you can kind of imagine the time kind of closing on itself as geometrically. So there are some models like that, but we don't really know what is the origin of time.
But you say the size of the world goes to zero, but again, does it have conflict with uncertainty for the...
No, I said when the size goes small. I didn't say zero. You said zero. I said when this universe gets smaller and smaller, it's effectively getting bigger and bigger. It's the opposite of what you're saying. So the examples we know in string theory is exactly the opposite. When you try to shrink it, it says, uh-oh, don't shrink me, I'm going to get bigger. So we don't know what happens there. Yes?
What is mass?
Yes?
What is mass?
Mass is energy, and energy is massive, yes. Sometimes we have learned to ask questions which have answers in the form of, ask me which experiment you want to do, and we try to give an answer. We try not to, that has been proven useful in physics, that we say, okay, we want to ask what does it make a difference? Tell me an experiment you have in mind, which I will try to answer it for you. So that translates a question which is philosophical to a question which is concrete, that we can say, oh, that's what I mean, and then we can give an answer yes or no, or this and that. Yes?
Are there any pre-assumptions for this theory?
Well, that quantum theory should exist, gravity should exist, which we know is true, both of them, and they should exist together. These are some preconceptions. Somebody asked, yes?
Sir, I remember you mentioned in therapeutic that even in my lifetime we can't reach the point that technology can observe the strings.
Not yet, yes.
Even in our lifetime.
Most likely.
So, have you done anything regarding this issue? I mean, with engineers or any...
Yes, I've become... No, I'm not...
is there any...
No, as I said, I've tried to change questions to questions that can have experimental verification, like cosmology I told you about, dark energy. So some things, the universe was small at some point. Okay, now big. Okay, does it have any predictions about string theory about it? Can we say, okay, this feature in the cosmology has something to do with string theory? These are the questions which are more practical. For us to make the technology or try to do that in our lifetime, say, okay, these engineers don't know what they're doing, I better change my field and do it. No. It's hard. It's not. I'm not belittling their work. It's hard. We can't do it.
And what is the... Sorry, because maybe a lot of my colleagues... what is the puzzle that you are now following? I mean, what is the thing that you are now following?
The thing I'm working on right now is related to dark energy, whether dark energy is constant or changes in time. So together with some colleagues, we have put forward the idea that dark energy is actually decreasing in time, and maybe that's true. We'll see in a few years. Maybe not. We'll find out.
Regards to human technology.
Okay, just 1 second. No, okay, go ahead.
Okay. You referred to this idea that engineers need to imply build bigger, more energetic machines.
I didn't say they need to. I'm saying we cannot do it with the current technology. I don't know what they should do or not shouldn't do.
Leading on to the next thing, could the future study of black holes and interactions lead to some experimental evidence which could support string theory?
Some people hope that. Some of my colleagues are trying to see some aspects of string theory about in the horizons of black holes and all that. It doesn't look likely, to be honest, but you never know. So I think right now I wouldn't bet on it. Yes?
Is dark energy concern?
Dark energy?
Is it concern?
No. Dark energy can change in time.
So what I'm saying is inside the universe.
No. Then the energy, when we say energy is conserved, we mean only locally. So in fact, the conservation of energy is not the principle of physics globally. The reason is that the conservation of energy has to do with time translation invariance, which means that if a process changes in time, energy is not conserved. And our universe is expanded, therefore energy is not conserved. Therefore, there's no conservation of energy as a whole. Let's do this. I'll give maybe 1 or 2 more questions and then we stop. So people who are tired, who want to go, they may not be too polite, they want to stand up and leave. They can leave, and if anybody wants to further ask, they can come in the front and we can ask. So 1 or 2 questions before we do that. Yes?
Does string theory say about anything about what the singularity of black hole?
The string theory tells you the singularity of black hole is just a phantom, but what aspect of it is a phantom, we still have to develop. Namely, we have dual descriptions of a black hole without any singularity. So there are some descriptions of black hole which doesn't have any problem with singularities. But there are some descriptions which do have singularities. So in that description, we don't have a good answer about what does that singularity mean. But there must be a resolution.
For instance, why does it have a charge?
Why does it?
Why does a black hole, how can it have a charge?
It can have a charge if you drop an electron in it.
Yeah, I understand, but how does it translate to string theory?
It does. You can just study. So a charge is like a string wrapped around a circle. And that's exactly how we counted the entropy of black holes in string theory. We counted how many ways you can wrap the strings around the extra dimensions. And that count gave you an entropy which Hawking had predicted. And that was one of the first predictions of string theory to derive Hawking's entropy. So last question then.
Well, actually, this is his question.
Fine.
You have 4 dimensions on the string theory. He was asking, you have your 3 major big dimensions. And then you have what? 4? You have
4 is the time.
4 is time.
And what is the other 5?
The other 5 are other space dimensions.
They're small, right?
They're small. Just like x, y, and z. X prime, y prime, z prime. Just gave it in what they're in. Thank you very much. I will stop here and say